All right, welcome back to the Explainer. Today, we're going to talk about this kind of hidden science that's like everywhere and shapes our world in ways you probably don't even realize. So, have a look at this: an aluminum can, a car battery, your smartphone. On the surface, what do they even have in common, right? One holds your soda, one gets your car started, and the other, well, it connects you to pretty much everything. But what if I told you that the very same fundamental science is behind all three of them? Yup, the answer is electrochemistry. It's this invisible force that literally creates, powers, and, as we're about to see, even destroys some of the most important things in our modern lives. So, what is it really? Okay, so let's dive in. We'll start with one side of the coin. Basically, chemistry by force. This is where we use electricity to make chemical reactions happen that, left to their own devices, just wouldn't. Think of it like this. It's kind of like cooking, but with electricity. You have these ingredients that just refuse to mix on their own. But if you run an electrical current through them in what's called an electrolytic cell, you can actually force them to react. You're basically giving the whole system this big electrical nudge to get things moving. And you know what? This is not some brand new idea. This goes way back to the 1830s with the absolute legend Michael Faraday. He's the one who meticulously figured out the rules of the game and gave us these laws that industry still depends on today. And his first law? It's so simple, but it's genius. It's basically a recipe. The amount of stuff you make is directly tied to how much electricity you put in. More current means more product. It's super predictable, you can scale it up, and yeah, it totally changed the game for modern industry. Okay, so what can you actually do with this power to force chemical reactions? Well, for starters, you can build our modern world, beginning with some of its most basic building blocks. Well, for starters, take copper refining. To get that super pure copper you need for electronics and wiring, you begin with a big, impure bar. That's your anode. You apply a current, and copper atoms literally dissolve off of it, travel through a special solution, and plate themselves onto a pure sheet, the cathode, leaving all the impurities, all the gunk behind. It's just a beautiful, elegant way to purify stuff on a massive scale. And it's not just copper. This principle is an absolute workhorse for industry. It's how we churn out huge amounts of other critical metals, like sodium, magnesium, and, yep, the aluminum for that can we started with. I mean, for some of these metals, this is literally the only practical way we can produce them. And just to give you a sense of the scale we're talking about here, a commercial plant can be using currents as high as 50,000 amps. To put that in perspective, your home circuit breaker probably trips at, 15, maybe 20 amps. We're talking about an insane amount of energy being harnessed to create the raw materials of civilization. All right, so that's how electricity can drive chemistry. But what about flipping that around? What about chemistry driving electricity? And that brings us to the electrochemistry you deal with every single day. Yep, we're talking about batteries. So when it comes to batteries, you can pretty much lump them into two big categories. You've got your primary batteries, like the one in a wall clock. The chemical reaction inside is a one-way trip. It happens once to give you power, and then that's it, it's done. But then you have secondary batteries, like in your car or your phone. Those are the really clever ones, because you can actually use electricity to reverse the chemical reaction, recharging it to be used again and again. At its core, a battery is what we call a galvanic cell. Remember how before we had to force a reaction to happen with electricity? Well, a galvanic cell does the complete opposite. It's designed to take a chemical reaction that wants to happen all on its own and harness it, converting the energy stored in those chemicals directly into a flow of electrons. And that's the electricity that powers our world. Okay, now let's take that battery concept and just push it into the future. What if you could have a battery that never, ever ran out of juice, as long as you just kept feeding it? Well, that's the whole promise behind the fuel cell. The key difference is this: a normal battery has all its fuel packed inside. A fuel cell is more like an engine. You feed it fuel, like hydrogen and oxygen, from the outside. And as long as you keep that fuel coming, you just keep getting electricity. It's awesome. One of the coolest examples ever comes from the Apollo space program. They used hydrogen-oxygen fuel cells for power on the spacecraft, but here is the absolute genius part. The only thing that reaction produced as a byproduct was pure water, which, get this, the astronauts could actually drink. Talk about an elegant, life-sustaining system. And when you look at the efficiency, it's just staggering. A traditional power plant that burns fuel to make steam to turn a turbine, it loses a ton of energy as waste heat. It's only about 40% efficient. Fuel cells, on the other hand, convert chemical energy directly to electricity, and they can hit efficiencies of around 70%. That is a huge, huge leap forward. So, we've seen how electrochemistry can create things and power our world. But, there's a dark side to all this. It's what happens when these exact same reactions happen on their own, uncontrollably, all around us. I'm talking about corrosion. And the scale of this problem is just mind-boggling. Corrosion is this relentless enemy that causes, and I'm quoting here, enormous damage to buildings, bridges, ships, and to all objects made of metals. It really is a slow-motion disaster that costs us billions and billions every single year. And this is the real kicker. Rusting is electrochemistry. When you see a piece of iron rusting, it's not just some surface stain. What's actually happening is a tiny, microscopic electrochemical cell has formed on the metal. It's like a tiny, self-destructing battery. So how does it work? Well, it happens in a few steps. First, one little spot on the iron acts as an anode and gives up its electrons, just like in our refining example. Those electrons travel over to another spot, the cathode, where they react with oxygen from the air. And then the iron ions left behind combine with oxygen to form that flaky reddish-brown stuff we all know as rust. So it's this incredible duality, right? The very same fundamental science that we harness to build our world, from pure metals to advanced spaceships, is the exact same process that is silently, relentlessly working to tear it all down. And all this leaves us with a big final thought. The hydrogen economy powered by clean fuel cells is held up as this great hope for a sustainable future. But the thing is, making all that hydrogen fuel, usually by the electrolysis of water, takes a massive amount of energy. So the real question is, how do we cleanly power the process that creates our clean fuel? That's the challenge and the opportunity that's still ahead of us.